A client sends a request to an address that, a moment earlier, was alive. The reply never comes. Not because the application vanished, because the thing that held the address vanished. In a Kubernetes cluster, that thing is a pod, a small disposable envelope around one or more containers. Pods are meant to die. They get rescheduled, they get replaced. Their IP addresses are not a promise. They are a temporary lease. That is the opening crisis of this story. Applications still need a front door. Users still need one place to knock. Other services still need a number they can write down and trust. But the rooms behind the door keep changing their street addresses. Imagine a hotel that rebuilds rooms overnight. Guests keep arriving with yesterday's room number. The night clerk shrugs. That is life without a service. Every replica of your application is a room that can disappear. Every client that memorized a pod IP is a guest holding a useless key. The question is not how to make pods immortal. Kubernetes does not want them immortal. The question is how to put something permanent in front of something temporary. How can an endpoint survive a disposable pod? What stands between that chaos and the client is a quieter object, one that keeps its IP even when the pods behind it do not. Before we name its types, sit with the stakes. If you get this wrong, internal traffic breaks when a replica restarts. External users hit a dead node. A demo works on Tuesday and vanishes on Wednesday because a virtual machine changed its address. This is a story about boundaries. Who is allowed to reach an application and through what kind of door? Private corridor, emergency side entrance, managed public gateway, or a name that does not lead to pods at all? The address that vanished is the problem. The service is the first answer. The type of service is the argument that follows. Watch a pod as if it were a person with a phone number that the carrier can revoke without warning. That is not a metaphor stretched for drama. It is how the cluster is designed. A pod gets an IP on a virtual network. Other processes can talk to that IP until the pod is gone. Then the number is recycled. A new pod, even one running the same container image, is a new endpoint. Why would anyone build a system this unkind to addresses? Because compute that can die is compute that can heal. If a node fails, the scheduler starts another pod elsewhere. If you scale from one replica to 3, you do not want clients hunting 3 new numbers. If you scale back, you do not want them calling ghosts. So the cluster treats pods as cattle, not as pets with engraved nameplates. That decision creates a networking debt. Someone still has to answer the phone. Someone still has to spread the calls when 3 copies of the same microservice are healthy. Picture 3 replicas of one application. Call them A, B, and C. A client that hardcodes A's IP is loyal to a single mortal. When A dies, the client is stranded even though B and C are fine. A client that tries to track all 3 must become a tiny inventory system, watching creations, watching deaths, rewriting its own configuration. That is not loose coupling. That is a marriage to chaos. The source of this problem is not malice. It is honesty about failure. Pods will die. The endpoint cannot be allowed to die with them. So the platform needs an object whose life is not tied to any one pod's life. An object that can keep a number while the rooms behind it are demolished and rebuilt. That object is about to walk on stage. And once it does, a second question appears. If the number is stable, who is allowed to dial it? A Kubernetes service is the stable front desk in front of disposable rooms. It provides a stable IP address to the pods. Even if a pod dies, the service and its IP stay. You do not have to change the endpoint every time a pod disappears. That single sentence is the whole reason this object exists. Think of the service as a published number that never belongs to one worker. The workers come and go. The number remains. Clients call the number. The service decides which living worker should take the call. This is more than convenience. It is an abstraction for loose coupling. The client no longer needs to know how many pods exist, where they run, or when they restart. It needs one contract, this service, this IP, this port. Behind that contract, the cluster is free to replace compute. The service's lifecycle is independent of the pods it fronts. That independence is the quiet revolution. You can delete a pod and the service does not mourn. You can add replicas and the service does not need a new identity. The front desk stays open while the staff rotates. There is a second gift hiding in the same object. A service is not only a nameplate, it is a distributor. When you have replicas, 3 copies of a microservice, for example, the service takes a request aimed at the application and forwards it to one of those pods. Clients call a single stable IP instead of calling each pod individually. So services are a good abstraction for communication inside the cluster and, depending on type, outside it as well. Notice the hinge in that sentence. Inside and outside are not the same door. Stability is one problem. Reachability is another. The service solves the first by existing. The type of service decides the second. We now have a permanent address. The next mystery is how that address shares the work. Load balancing here is not a cloud product with a brand name. It is a simple fairness. One published address, many possible hands. A request arrives at the service. Behind the service sit pods that match. The service forwards the request to one of them. A next request may go to another. Clients never choose the replica, they choose the service. Why does that matter in the body, not just in theory? Because replicas exist for 2 human reasons: more capacity and survival. If every client pinned itself to one pod, extra replicas would sit idle until someone updated a spreadsheet of IPs. If that one pod failed, those clients would fail with it, while healthy twins waited unused. The service collapses that waste. One IP, many backs. Listen to the causal chain. Pods are temporary. Temporary things cannot be the public identity of an application. A service becomes that identity. Once identity is centralized, distribution becomes possible. You cannot load balance what you cannot name. The source puts it plainly. When you have pod replicas, the service gets the request targeted to the application and forwards it to one of those pods. Because of this, clients call a single stable IP address instead of calling each pod individually. Feel the relief in that design. The application team scales the deployment. The networking identity does not change. The on-call engineer restarts a crashing pod. The clients do not rewrite their configs. The service is the shock absorber between human operations and machine mortality. But a shock absorber is not a wall. A stable IP can still be a private IP. It can still be a port on every machine. It can still be a public address handed out by a cloud. Stability without a boundary policy is an unfinished story. The next chapter asks who is allowed through the front desk and draws 3 doors. Picture 3 doors on the same building, same application behind them, different keys, different weather on the outside. The first door opens only onto the interior hallway. If you are already inside the cluster, you can walk through. If you are on the public internet, you cannot even see the handle. That door is cluster IP. The second door is bolted onto every exterior wall of every building in the complex. Same number painted above each bolt. Anyone who can reach a node's address and that number can get in. No fancy canopy, no attendant. That door is node port. The third door is a proper entrance with a canopy the cloud provider built for you, a public IP. Traffic lands on infrastructure that is not a random virtual machine you happen to SSH into. That door is load balancer. These are not 3 random products. They are 3 answers to one political question. Where does the cluster end and the rest of the world begin? Cluster IP says the world does not come in. Other components of the same application may talk. Internal dashboards may light up. Debugging may happen through a proxy. The street stays outside. Node port says, we will cut a hole in every node. It is primitive. It works. It has costs we will count later. Port ranges, 1 service per port, addresses that can move. Load balancer says, ask the underlying cloud, such as AWS, GCP, or Azure, to provision a load balancer and assign a public IP. External users arrive through that IP. A comparison table would line them up by accessibility, use cases, whether they load balance, what kind of IP they offer, and how they scale with the application. Accessibility is the column that decides the plot. Internal only. External through a static node port. External through a provisioned balancer. There is a 4th character waiting in the last act. A service that does not lead to pods at all, only to a DNS name outside. But we should not meet it yet. First, walk through the private corridor. It is the default. It is the most common. And it is the door most people accidentally leave closed when they expected a street. Cluster IP is a type of service that exposes an internal IP address within the cluster. That sentence is the entire personality of this door. Internal, within, not on the sidewalk. It enables communication between different components of an application deployed inside the same Kubernetes cluster. A front end talking to a back end, a worker talking to an API, a dashboard that should never be a public website. Those conversations need a stable name, but they do not need a public address. Cluster IP services are typically used for internal communication between pods. They are not accessible from outside the cluster. No external process. If you are standing on the internet with a browser, this IP will not answer you. That is not a bug. That is the lock on the corridor. Why start here, historically and practically? Because most traffic in a real system is not tourists. It is rooms talking to rooms. If every internal hop required a public load balancer, you would publish your plumbing. You would also pay for doors you do not want opened. So cluster IP draws a hard line. The service still has a virtual IP. The service still load balances among matching pods. The service still outlives those pods. But the audience for that IP is the cluster itself. Imagine a hospital. The public can reach reception. They cannot wander into the pharmacy phone extension. Cluster IP is the pharmacy extension, essential, unlisted on the highway sign. When people first meet Kubernetes, they often create a deployment, then wonder why the world cannot curl it. They created rooms. They may even have created a service. If that service is cluster IP, and it often is, they built a perfect internal phone system and then stood in the parking lot waiting for it to ring. The next fact makes that surprise almost inevitable. Cluster IP is not just common. It is what you get when you forget to ask for anything else. Cluster IP is the most common service. It is also the default type. When you create a service and do not specify a type, the cluster automatically takes cluster IP. Forgetting is a choice. The platform chooses the private door. That default is a safety story as much as a convenience story. The safer assumption is, do not publish this. Let internal components find each other. Make exposure an explicit act. How does traffic actually find pods? Several pods that satisfy a label selector can handle incoming traffic thanks to the load-balanced IP address cluster IP provides. The service does not hard-code pod names, it selects. Labels are the handshake. If a pod wears the right labels, it is eligible. If it does not, the front desk will not send it guests. To forward TCP or UDP communication to containers, this service needs one or more ports for listening, with destination ports provided. In plain language, you declare where the service listens and where the container should receive the traffic. The virtual IP is useless without those ports. A front desk with no extension numbers is just furniture. This is the default service type that exposes the service on a cluster internal IP, making the service only reachable within the cluster. A cluster IP service gives you a service inside your cluster that other apps inside your cluster can access. Hold those pieces together. Default type, label selector, listening ports and destination ports, internal IP, no external process. That is the complete machine for the private corridor. Now the human scenes where this machine is the right tool. Debugging. A laptop connecting through a proxy, internal dashboards, traffic that should never leave the building. Those uses are not lesser uses. They are most of a platform's real life. The hook is simply this. Once internal traffic is solved, an outside user still cannot reach the service. Someone, sooner or later, will want a hole in the wall. When would you choose this locked corridor on purpose, not by accident? The source names a few scenes. You might use the Kubernetes proxy to reach your services. You might be debugging. You might connect to them directly from your laptop for some reason. You might allow internal traffic only. You might display internal dashboards. Each of those scenes shares a moral. The audience is trusted, or at least inside the same administrative world. A dashboard of cluster health does not need a billboard on the highway. A backend that only the front end should call does not need a public IP. A broken service that an engineer must inspect may be reached through a proxy rather than through a permanent public door. There is dignity in that restraint. Not every application wants to be famous. Many want to be reliable among friends. Consider an internal dashboard. It still needs a service. Pods still die. Replicas still need balancing. Cluster IP gives it all of that without inviting the planet. Consider two microservices that only speak to each other. Cluster IP is the hallway between their rooms. Consider a developer who needs 5 minutes with a process. A proxy into cluster IP is a visiting badge, not a new public entrance. The limitation is the same fact that makes it safe. There is no external process. If product wants customers on the internet, cluster IP alone will not carry them. If a partner needs an API from another network, this door stays shut. So cluster IP wins the first battle, the vanishing pod address among internal callers, and loses the second on purpose. The application is findable, it is balanced, it is not public. That loss is the cue for a more primitive character, a port carved into every node, like a side door with the same number painted on every wall. It is not elegant, it is how traffic first learns to leave the building without asking a cloud for a canopy. Node port is a type of service that exposes a port on every node in the cluster. Read that again, slowly. Not one node you picked, every node. The cluster punches the same hole through each machine. It allows external access by forwarding traffic from the specified port on each node to the corresponding port on the pods targeted by the service. You do not need a load balancer from a cloud vendor to make this work. That is the temptation. Reach the application from outside it without provisioning extra infrastructure. This exposes the service on each node's IP at a static port. Static is the word that matters. The port does not wander every time a pod restarts. You can tell a colleague, hit this machine, this port. The colleague is no longer chasing pod IPs. And here is the hidden architecture. A cluster IP service to which the node port service will route is automatically created. Node port is not a replacement that throws the private corridor away. It is a second door that leads into that corridor. Outside traffic hits the node port. Then it rides the internal service toward the pods. We can contact the node port service from outside the cluster. That sentence is the whole plot twist after cluster IP. The hallway now has a street-facing hatch. A node port service is the most primitive way to get external traffic directly to your service. Primitive is not an insult in this story. It is a warning and a compliment. It works with very little ceremony. It also inherits the roughness of something improvised. As the name implies, it opens a specific port on all the nodes, the virtual machines, and any traffic sent to this port is forwarded to the service. Same number on every wall, same destination inside. Primitive doors have rules. The next chapter is those rules, and they are sharp enough that the source does not recommend this as your production front of house. Stand outside the cluster. You know a node's address, a virtual machine on a network you can reach. You know a port number that node port reserved. You send traffic there. The node accepts it on that port and forwards it to the service. The service, still doing its original job, forwards it to a matching pod. That path has 3 hops of meaning. First, the node is now part of the public identity. Not the pod, not only the virtual service IP. The machine itself is a doorway. Second, every node is a doorway with the same port, so you are not required to guess which machine holds the pod. Third, the inner cluster IP still load balances. The primitive outer door does not replace the front desk, it feeds it. This is why node port can feel magical in a demo. You expose a deployment. You type a node IP and a high port into a browser. A page appears. Pods can crash behind the scenes. The port on the node remains. For a moment, the vanishing address problem looks solved for the outside world. But look at what you have made the client depend on. Not a cloud-assigned Anycast VIP, a node IP plus a port. If you have several nodes, you might pick one and hope it stays. You might put something else in front yourself. The service type did not give you a managed front door. It gave you a consistent hole. Remember the automatic cluster IP. Internal callers can still use the private IP. External callers use node plus port, 2 audiences, 1 set of pods. That is elegant until the constraints arrive. The constraints are not footnotes. They are the reason this door is an emergency exit more than a lobby. 1 service per port, a narrow band of legal port numbers, a dependence on the node or VM address remaining the address you published. Count those costs one by one. They change the recommendation from "this works" to "this works when you can live with the bill." There are many downsides to this method. The source does not soften them. You can only have one service per port. Ports are not an infinite public park. If this service claimed 30012 on every node, another service cannot claim the same number. The cluster's exterior walls have a limited number of numbered hatches. Each hatch is exclusive. You can only use ports 30,000 through 32,767. That range is the legal neighborhood for these hatches. It is not the familiar 80 or 443 of the public web. Clients see unusual numbers. Firewalls must allow unusual numbers. Humans must remember unusual numbers. The door is visible, but it looks like a service entrance because it is one. If your node or VM IP address changes, you need to deal with that. Here the old curse returns in a new costume. You escape the pod's disposable IP. You change yourself to the machine's IP. Machines move. Cloud instances get replaced. Networks get renumbered. Yesterday's curl command becomes archaeology. For these reasons, the source does not recommend using this method in production to directly expose your service. That is a strong line. Direct production exposure is the thing this door is worst at pretending to be. Why? Because production usually wants more than a packet can arrive. It wants a stable public identity that is not a random virtual machine. It wants familiar ports. It wants many services without playing musical chairs on a 2,768 number range. It wants the node fleet to be replaceable without rewriting every partner's bookmark. Node ports solve the outside the cluster problem the way a crowbar solves a locked door. Effective, loud, not what you install on a flagship store. And yet the same paragraph that warns you also offers a pardon. If the application does not have to be always available, or you are very cost sensitive, this method will work. A demo, something temporary. That pardon is the next scene's entire weather. When is a crowbar the right tool? When the application does not have to be always available, when you are very cost sensitive, when the thing you are showing is a demo or something temporary. Those are not insults to the work, they are honest scopes. A demo exists to be seen this afternoon, not to be bookmarked for 3 years. A temporary environment exists to prove a point, then disappear. In those worlds, provisioning a cloud load balancer may be slower than the meeting. It may cost money you do not want attached to a throwaway namespace. Node port says, open 30,000 through 32,767 on the nodes you already have. Send people a node IP and a port. Let them in. Cost sensitive is a real constraint, not a personality flaw. A managed load balancer is extra infrastructure. Extra infrastructure is extra invoice. If the audience is a handful of testers on a private network that can already reach the nodes, paying for a public canopy can be theater. Not always available is equally honest. If a node IP change would be annoying but not a contractual incident, you can live with the third downside. If one service per port is fine because you have one demo, the first downside vanishes. If clients can tolerate a high port number, the second downside is just aesthetics. So node port is the emergency side door that is allowed to remain in the building code. Use it when the vanishing pod problem must be solved for outsiders, and the outsiders are temporary, cheap, or both. What it will not do is retire the deep need. Public web applications, partner APIs, fleets of microservices that must remain reachable while nodes come and go, those want a door whose address is not a VM lottery. That door has a name that sounds like the function we already met. Load balancing as a service type, not only as a behavior. The cloud, this time, builds the canopy. Load balancer is the service type that exposes an application running in the cluster to the outside world, not through a hatch on every node, but through infrastructure the cloud already knows how to run. When you create a load balancer service, Kubernetes provisions a load balancer in the underlying cloud infrastructure, such as AWS, GCP, or Azure, and assigns it a public IP address. External users access the application using this IP address. Here the shift in identity. With cluster IP, the identity was a virtual address only the cluster could reach. With node port, the identity was every node's IP plus a high port. With load balancer, the identity is a public IP on a provisioned balancer. The nodes can still churn. The pods can still die. The published number belongs to a different layer. This is commonly used for applications that need to be publicly accessible, such as web servers or APIs. The street is supposed to find you. The type matches that intention. Notice what Kubernetes is doing. It is not merely opening a port, it is asking the surrounding world to allocate a device, or a managed equivalent, whose job is to receive the internet and hand traffic inward. The cluster remains the place pods live. The cloud remains the place public IPs are minted. That division of labor is why this type feels like production's native language. You are no longer pretending a virtual machine is a storefront. You are requesting a storefront. The vanishing address problem is solved again at a higher altitude. Clients do not memorize pods. They do not even have to memorize a particular node. They memorize the public IP the balancer received, or a DNS name you later attach to it, though that naming is a neighboring story. A public IP is a powerful object. The next question is not how it is minted. It is who should be allowed to stand behind it. A website, an API, a mesh of microservices, a system that must stay up when pods fall. When should you ask the cloud to build that canopy? Public-facing web applications. If a web application needs to be accessible over the internet, a load balancer service can expose it to external users. This is the obvious case, and obvious cases still deserve precision. The users are not other pods. They are people and browsers and crawlers. They should not be told to hit port 31234 on a node that might be replaced tonight. API services. When APIs must be consumed by external clients, a load balancer service can provide a stable endpoint for accessing those APIs. Partners, mobile apps, other companies' servers, they want a number that behaves like a contract. Stability here is social as much as technical. You published an endpoint. You do not get to change it because a pod restarted. Microservices architectures. In systems where different services communicate over the network, load balancer services can expose individual services to other services within the cluster or to external clients. That sentence from the source is wider than the street. It admits this type can face inward or outward depending on who must consume the endpoint. The distinctive gift is still the provisioned balancer and the address it carries. These uses share a demand that node port only half meets, an entrance that looks like infrastructure, not like a hole. They share a demand cluster IP refuses. Someone outside the private corridor must get in. Choose load balancer when the application's job is to be found by a world that should not know your nodes. Choose it when the endpoint is part of a product, not part of a lab. The remaining use case is not a kind of application. It is a kind of weather. High availability. Traffic distributed across multiple pods or replicas, so the application remains accessible even if one or more pods fail. We have seen that behavior since the first chapter. Here it is named as a reason to pick this public door. Availability is the promise you make after the address stops vanishing. High availability in this telling is not a mystic property of the cloud logo. It is the old load balancing gift raised to a public entrance. Load balancer services can help improve the availability of your application by distributing traffic across multiple pods or replicas, ensuring the application remains accessible even if one or more pods fail. Translate that into the hotel again. Many rooms, one canopy. If a room is condemned, guests still arrive at the canopy. The clerk sends them to a living room. This is the same logic cluster IP used internally, and the same logic node port borrowed when it forwarded into an automatically created cluster IP. The difference is who gets to stand in the rain and still find the canopy. External users, public clients, the internet. Availability has two enemies we have already met. Enemy 1, a single pod as the identity. Kill it and the application disappears. Enemy 2, a single node IP as the identity. Lose the node and the published path disappears even if pods are healthy elsewhere. Load balancer aims the client at a provisioned balancer with a public IP, then lets the service continue spreading work across replicas. It does not make pods immortal. It makes their deaths less visible. That is the only immortality operations can honestly sell. There is a boundary this type does not cross. Not every dependency lives inside the cluster. Some databases, some legacy systems, some SaaS endpoints already have names on the public DNS of the world. You may want your in-cluster applications to call those names as if they were services, without pretending they are pods, without load balancing replicas you do not run. The three doors were all about traffic toward pods. The last character in this story turns away from pods entirely. It is a service that is only a name, an alias, a pointer to somewhere else. External name. The front desk that says, the thing you want is not in this building. External name is another kind of Kubernetes service. It lets you map a Kubernetes service to a DNS name outside the cluster. It does not open a cluster IP corridor to your pods. It does not punch node ports. It does not provision a cloud load balancer. It offers a DNS alias for an external resource, so workloads inside the cluster can reach something hosted outside as if they were calling a local service. That is a different kind of stability. Not a virtual IP in front of replicas, a name in front of a name. Why would you want that? Because applications inside the cluster still like Kubernetes-shaped dependencies. They look up a service. They live in a namespace. They should not all hard-code a foreign hostname in a dozen places if you can give them one in-cluster name that points out. The source gives a concrete pairing. A service definition associates the external DNS name my.database.example.com with the prod namespace service my-service. That implies my.database.example.com will be the destination for any requests made to my-service inside the prod namespace. Here the geography. Namespace, prod. Service name, my-service. Foreign shore, my.database.example.com. The cluster does not claim to run that database as pods. It claims to know what the name means. This is the plot twist that keeps the documentary honest. Not every important process is a replica you schedule. Some important processes were already running before your cluster existed. External name is how the service abstraction bows to that fact instead of denying it. It is also a reminder that service was never only load balancer. From the first chapter, a service was an abstraction for loose coupling. Sometimes loose coupling means many pods behind one IP. Sometimes it means one local name for a distant system. The next scene is the actual document of that alias, the YAML fields exactly as written, because a DNS pointer is a place where a single misspelled host becomes a silent outage. Here is the service definition, field by field without decoration. API version, v1. This object speaks the core Kubernetes API. Kind, service. We are not looking at a deployment or a pod. We are looking at the abstraction this whole film has been about. Metadata.name, my-service. That is the in-cluster name callers will use. Metadata.namespace, prod. Names are local to a namespace. My-service in prod is not automatically my-service anywhere else. The alias lives in a neighborhood. Spec.type, external name. This is the line that changes the meaning of everything else. Not cluster IP, not node port, not load balancer. External name. Spec.external name, my.database.example.com. That is the foreign DNS name. That is the real destination. Together they say, inside prod, my-service means my.database.example.com. Requests made to my-service inside that namespace are aimed at that external DNS name. There is no label selector in this story. There is no replica set of database pods implied. The service is a pointer. Why walk the YAML this slowly? Because types are easy to confuse when they share a kind. A service named my-service could have been a private IP. It could have been a node hatch. It could have been a public balancer. The type field is the plot. The external name field is the destination. Mix them up and you either publish something you meant to alias or alias something you meant to load balance. The hostname itself is a character, my.database.example.com. It sounds like a database living under an example domain, exactly the sort of thing a cluster might depend on without owning. We now have 4 answers to the vanishing address. 3 of them front pods at different perimeters. 1 of them refuses to front pods at all. The last chapter has to cache the opening stakes. The client still needs a door. Which door? The address that vanished was never going to be saved by making pods immortal. It was saved by putting a service in front of them, a stable IP, a load balancing front desk, a life cycle that does not die when a replica dies. Then the story became a story about boundaries. Cluster IP is ideal for internal communication within the cluster. It is the default. It selects pods by label, listens on ports, and refuses the outside world. It is how rooms talk to rooms. Node port allows external access without a load balancer. It opens the same static port on every node, feeds an automatically created cluster IP, and works. It also allows only one service per port, only ports 30,000 through 32,767, and it ties you to node or VM IPs that can change. Demos, temporary apps, cost-sensitive cases. Not a recommendation for directly exposing production. Load balancer is suitable for publicly accessible applications. Kubernetes provisions a balancer in the underlying cloud, AWS, GCP, Azure, and assigns a public IP. Web applications, APIs, microservices that must be reached, higher availability through distribution across replicas. External name maps an in-cluster service to an outside DNS name, such as my-service in prod, pointing at my.database.example.com. No pods required. An alias instead of a door. By selecting the type based on the application's requirements, you optimize how traffic arrives and how much of the world is invited. The opening crisis resolves. Unstable compute can look stable. The unresolved question is the one operators still chase as systems grow. Which boundary best balances reachability, resilience, and control? Too private and customers cannot enter. Too primitive and a node change becomes an outage. Too public and you publish plumbing. Too many aliases and you no longer know what you actually run. The client is still at the desk. The rooms are still being rebuilt. Choose the door on purpose.